Today's video is part 2 of section 1.4, continuity. The homework is 33 through 48, all, 57 through 60, all, and a handout. So let's talk about first removable discontinuities. The definition of a discontinuity is at x equals c is called removable if f of x can be made continuous by defining f of c. What does that mean? So here I have some function with a hole. It is discontinuous. And so if I could just fill it in with just one single dot, and of course it's bigger just so it's exaggerated so you can see it, but if it can just be filled in and now it's continuous everywhere, then this is called a removable discontinuity. If I could just take my pencil, put one dot, and it would be continuous all the way through, then this is called a removable discontinuity. So graphically, what does this look like? Well, I just have it up here. There is just a single hole in a smooth curve. Then that hole, or at that value C, is a removable discontinuity. Well, what does that single hole look like algebraically? And we learned this in pre-calculus last year. When you factor, you can cancel out a removable discontinuity. Or in other words, when you factor out a term in the numerator denominator, it is a hole. Let's review an example from pre-calculus. We have this function, x minus 5 over x squared minus 25. And so I'm going to go ahead and factor it out, difference of squares. I'm able to cancel out the factor x minus 5. What that means is the term x equals 5, which makes that go to 0, that was a hole. The factor that you can cancel is a hole. So that's just a hole in the graph. This would be a removable discontinuity. But this term that is left, the x plus 5, well, that x equals a negative 5, what makes this factor go to 0, ends up being a vertical asymptote. And we did this last year. So this part here is the removable discontinuity. So let's look at what are not removable discontinuities. So again, I'm talking about where it's not continuous, but now where it's not removable. And that's in two places, in my jumps and my vertical asymptotes. So for example, in this function here that we just learned about, the absolute value of x minus 2 all over x minus 2 is sketched out as such. And so I can't literally take my pencil and fill in one point and make that a nice smooth curve now. So therefore, x equals 2 is not a removable discontinuity. Over here, 1 over x plus 2. Well, this is a factor I cannot cancel out. So when x equals negative 2, which makes this go to 0, that happens to be a vertical asymptote. So there's no way in this graph I can just make one point and that would connect this graph and be nice and smooth. Therefore, x equals negative 2 is not a removable discontinuity. Again, one more time, the only time is when I have a hole in a nice smooth curve. I can just fill it in and now it's smooth. That is a removable discontinuity. Again, that's how you find your hole. So let's look at a set of directions in your homework and work through how you might do these. In 33 through 54, it says, find the x values, if any, at which f is not continuous. And of those values, which of these discontinuities, which is what these are in the first sentence, are removable? In other words, which of these are holes in the graph and not jumps and not asymptotes? So we have to go back and do some pre-calculus work. So where can a function be discontinuous? At a hole, at a vertical asymptote, and at a jump. Which discontinuities are removable? Only the holes. So, an example, I'm going to pick on that problem again. The function x minus 5 all over x squared minus 25 that the x equals 5 is a whole. Why? Because I can cancel out that factor. And x equals negative 5 is a vertical asymptote. So again, this is removable. This is not removable. Let's look at this function. X all over x squared plus x. In fact, it might help if I did this. So I went ahead and I factored out the factor in the denominator, so it's x over x times the quantity x plus 1. So now I can clearly find the holes in the vertical asymptotes if there were any. So x equals 0 is my whole. Why? Because I can cancel out those factors in the numerator and denominator. This factor in the denominator is left. So x equals negative 1 is a vertical asymptote. And this is how you would sketch out that graph. So the vertical asymptote is at negative 1, but I may not use the value 0. So when you get to the x value 0, there is a hole. So this is a removable discontinuity. This is not. Jumps found in piecewise functions. That's where you're going to find the jump. So for example, the function x plus 1 as x is greater than or equal to 0, or the other piece of the function is the horizontal line negative 2 when your x or your domain is less than 0. So your jump at x equals 0, that is your discontinuity, and it is not removable. Why? Because I cannot just put in my point and it's all connected and smooth. Next set of directions. In the homework 57 through 60, it says, find the constants a and b so that the function is continuous everywhere. So this is actually one of your homework problems, and then you're going to have a handout, just as you did in pre-calculus, on these type of functions where you have to find the constants a and b or possibly c. I have a piecewise function. The domain has broken this up from negative 1 and everything less than that, between negative 1 and 3, not including those endpoints, and then 3 and greater than 3, we have two horizontal lines and we have a linear function. Except I don't know the values a and b. And so what I want to do is I want to find constants for a and b in which this function will be continuous everywhere. That means there will be no holes, no jumps, no asymptotes. So first off, if you look at this piece, that's a horizontal line y equals 2. This is a horizontal line y equals negative 2. So this here is a linear function. This linear function needs to connect these two pieces because they're in the middle. So this is continuous everywhere. This piece is continuous everywhere. This piece is continuous everywhere. The only place that we don't know is at negative 1 and at 3. And we're going to force it to be continuous. So how are we going to find out these values or these constants for a and b? We're just going to go ahead and we're going to use the definition. Finally, we're going to use the definition of continuity. So I'm going to first check out x equals negative 1. Or not necessarily check it out, but I'm going to go through the process. So by the definition of continuity, it has to satisfy 3 steps. When it satisfies 3 steps, it is continuous at that value. So the first step is that f of a exists. What is my a in this one? Negative 1. So f of negative 1 must exist. So when I look at this, it goes into this function. It happens to be 2. B, the limit of f of x as x approaches negative 1 also must exist. Well, because it's a piecewise function, I have to check the right and the left. So I went ahead and I did that. And so I chose negative 1 from the left. I went and looked at which piece of that function that would be. Negative 1 to the left. Here's negative 1 to the left. Here's the piece. That's why I wrote that there. I found the limit. It is 2. Lift that up a little bit more. The second one, the limit as x is approaching negative 1 from the right. Well, this is negative 1 from the right. That's just above negative 1. I'm going to use this piece. Now, don't worry about that. You don't know what this is. You already know this limit is 2. When you put in negative 1 for x, it is now negative a plus b. Well, by the definition of continuity, part C says that part A and part B have to be equal. Therefore, this has to equal this. So I know that the limit exists because I'm forcing it to be, and it's going to be 2. These two are both equal. So then I know something about negative a plus b. I know 2 must equal negative a plus b. It must, for this limit to exist, for it to be continuous at negative 1. Here's my first equation. I have 2 unknowns. I need a second equation. That must mean what I'm going to do is I'm going to check out this value and go through the same process. So let's do that. So for x equals 3, the first thing I do is I do f of 3. F of 3. So let's see. Back on my piece for 3. Oh, here's what I'm allowed to use. So the function, that piece is negative 2. B, the limit of f of x as x approaches 3. Well, because I have a piecewise function, I must do the right and the left. So let's do 3 from the left. 3 from the left. Here is 3 from the left. I'm going to use the piece ax plus b. That's why this is written here. Now I'm going to evaluate this limit, put 3 in for x. That's 3a plus b. I must find out what this equals. I already know it's got to equal a negative 2. Now 3 from the right. 3 from the right, negative 2. So again, I am forcing this to be continuous at x equals 3, which means this and this must be equal. That's what part C is about. Part C says that this and the limit of f of x as x approaches 3 must be equal to each other, and they're going to equal negative 2. Therefore, I have a second equation, second unknown. 3a plus b equals a negative 2. Now back from Algebra 1, I'm going to do 2 equations, 2 unknown. There's my 2 equations that I gathered. So I went ahead and I chose this equation first. I put in 2 plus a equals my b. What I did is I substituted that in here so all my variables are a, which is what I did, right? So 3a plus 2 plus a equals negative 2. So I took off the parentheses, combined like terms, solve for a. I have a. I have my first a. That's what is asked for. That's what the directions. Find the constant a and b. I have this. Back in Algebra 1, what you did then is you took this value, substitute back into the other equation to get your b, which is what I did here. 2 plus a equals b. Now it's 2 minus 1 equals b, therefore 1 is b. I am now done. Thank you.